Hi, I'm Jules Kyle, and this is my presentation on hybrid aluminum matrix nanocomposites. Hybrid aluminum matrix nanocomposites are part of the hybrid metal matrix composite family, which is classified as metal matrix composite reinforced by two or more reinforcement or dispersed phases. In this example, the two dispersed phases are tungsten disulfide and carbon nanotubes, otherwise known as C&T. One benefit that comes of this nanocomposite is the thermal stability. This sample performed better at keeping its weight percentage above the non-hybrid sample at temperatures leading up to 700 degrees Celsius, proving that this composite has a higher thermal stability compared to the components that make up this composite. Fabrication begins with 99% aluminum powder, multi-walled carbon nanotubes, and tungsten powder. These materials are then hot pressed together under vacuum conditions of 150 megapascals of pressure, 500 degrees Celsius, a heating rate of 15 degrees Celsius per 1 minute to the -1 for 40 minutes. The pressure was created by pumping argon and sulfur gas into the vacuum furnace to cause a reduction reaction with the tungsten. The final product is tablets 10 millimeters in height and 25 millimeters in diameter. It is then polished by a 20 micron aluminum oxide powder. The microstructure of this nanocomposite is formed by the one-dimensional nanostructures of the tungsten disulfide and carbon nanotubes. The addition of the carbon nanotubes causes the grain to become finer, but increases the thickness of the grain boundaries. But with proper distribution of nanoparticles in the matrix, the load transfer from the matrix phase to the dispersed phase will greatly improve due to the larger surface area of the nanoparticles. The mechanical properties of hardness, relative density, and compressive strength are also greatly improved by creating this composite. The hardness was increased by the addition of nanoparticles to the aluminum matrix, and its relative density was affected by the vast surface area of the nanoparticles, causing greater interparticle friction, thus creating cavities inside and between the grains, making it have a higher compressive strength and a lower relative density than the pure aluminum sample. These graphs show the relative density, hardness, and compressive strength versus the pure aluminum samples for the hybrid aluminum matrix nanocomposites. If you look closely, there is a red circle on each y-axis that represents the values of the pure aluminum sample versus the black line, which is the hybrid aluminum matrix nanocomposites.